G'day. Welcome to Crystal Clear Mathematics, where it is easier than you think. I'm Graham Henderson and we're continuing our series on asymptotes. Now in the last video we got a bit adventurous and we started discovering that asymptotes could not just be horizontal or vertical, but we can have oblique asymptotes and even curvilinear asymptotes, that is where the curve becomes asymptotic to some other curve off to infinity. And we created some rather nice and interesting graphs, and I encourage you to go exploring. Well, in this video we're going to discuss double and triple and quadruple asymptotes. Again, this is not something certainly it's not taught in New South Wales schools, but we're going to start by looking at a very, very simple hyperbola. xy equals 4. This is one we've graphed a number of times in the past. And let's just plot the points. Goodness, it's wild and woolly outside. You can probably hear the wind chimes I have outside and a bit of the wind, and we got sirens and things, so do excuse some of the background noises. Here we have a product of numbers making 4. So we have 2 times 2 makes 4. I should write the numbers in. 1 times 4 makes 4, and 4 times 1. So this is one part of our curve. And the other part is -2 times -2 makes 4, -4 times -1, and -1 times -4. So we get another part of the curve here. So far so good. Question. And remember, in previous videos I've said that mathematicians like asking questions like, what if? What if we did that? What difference would it make? What it means is that x equals 0, which is this asymptote, that's this asymptote, becomes what's called a double asymptote. Now I'm going to take you back a little bit to your understanding of polynomials. If you had a polynomial like y equals x minus 2 times x plus 1, you knew that it went through 2 and -1. You can see the parallels here, and it looked like this. But if I actually had a double root at 2, it came down, but it didn't go through the axis, it just bounced off like a parabola, which is exactly what it is. If I had both roots, but this one was doubled, this looks a bit messy, but what would happen is the curve would come down, it would arrive at the 0 of 2, and it would behave like a parabola at that point and bounce off, and then it would curve around and come back down through the other root at -1. And this was a way of graphing what is now a cubic function. But when we double a 0, the curve bounced off. So in other words, it was kind of duplicated around that point. Now exactly the same thing happens when we duplicate an asymptote. It becomes like a mirror. And this part disappears. This part of the curve becomes mirrored in the asymptote, and we get this. Now because of the squaring, these points move a little bit. So it's not the same shaped curve exactly as it was before, but it is symmetrical about that vertical asymptote. That's the consequence of doubling an asymptote. So let's experiment. Let's do one or two more of these. Well, let's be a bit adventurous. I'm going to stick with vertical and horizontal asymptotes for the moment, for this one. And let's make two vertical and two horizontal. So for vertical asymptotes, we might have x minus 2 and x plus 3. And for horizontal asymptotes, we might have y minus 1, y plus 2, and we'll set this equal to 3. One, two, three, four, 5. 1, 2, 3, 4, 5. Now let's mark where these asymptotes are. We've got one asymptote where x equals 2. So I'll just draw this down here. X equals 2. We've got another asymptote where x is negative 3. That's here. Another asymptote where where y is equal to 1. And another asymptote where y is equal to negative 2. Now again, our hyperbola will start here, and normally it would follow a checkerboard pattern. Just go diagonally through these points. But I'm going to double a horizontal asymptote, I'm going to double a vertical one. I don't particularly care which, so I'll do that. Now if I double the x equals 2 asymptote, it's this one. I think I'll try and go over this, or next to it in red. This is going to be a doubled asymptote. And y equals negative 2 is going to be a doubled asymptote. So let's see if we can plot out this particular graph. It's going to start here, because it's a positive 3, and the coefficients are all positive. But because this is a double, it's now going to be symmetrical about this asymptote. Now, of course, it can't be perfectly symmetrical because it's got another asymptote over here, so it's actually going to come down and back up there. Now here, of course, it will, these are just normal asymptotes, so it'll work diagonally across here. What's going to happen here? Well, this is going to duplicate whatever's on the other side. So this is actually going to be duplicated across the boundary. There was no graph here to be duplicated, and there was no graph here to be duplicated. So here we have a rather unusual sort of graph. This part certainly looks like a function, but this most certainly is not. And that would be the graph of that particular equation. I hope you're seeing the principle involved. Let's do something a bit more challenging and ask, what if we do this to a curvilinear or an oblique asymptote? Let's have a look. First we'll try this one. Let's put our circle down, x squared plus y squared minus 4. and our y minus x, y plus x equals 3, for example. And you might recall that when we graphed this in the last video, that this gave us a circle with a radius of 2. This gave us an asymptote. This behaves like an asymptote, by the way. This gave us an actual asymptote where y equals x. And this gave us an asymptote where y equals negative x or minus x. And as it stands, with a positive value here, the curve will start here, and then it will go diagonally across, so we'll have it here, and then in this region, and this region, and then here. Now, you'd have to see my last video to follow why that is. But what we're going to do is not duplicate one of these asymptotes, but double the circular asymptote. That's being a bit brave of us. What it means is that this, changing colours all the time here, it means that this one is going to behave like a mirror for the curve as it immediately approaches it. Let's see what that means. Well, still, the curve is going to exist out here. It'll be a slightly different shape because of the extra powers here squaring this term. But there it is. Now, because we've now doubled this asymptote, now again I agree it's not an asymptote but it behaves like one, because we've doubled it, this boundary behaves like a mirror for this part of the curve, so the curve actually exists here. Let's draw it in. It can't escape from these asymptotes. These are normal asymptotes, so diagonally across we have another portion. And again, the circle is behaving as a mirror for this bit, so we have more of it here. So what we've succeeded in doing, if you compare this with the graph we drew in the last video, is these two parts of the graph, instead of being here, are now here. And that's, apart from a slight change in the shape of the curve, that's the major feature change that we would see by squaring this particular, or doubling this asymptote. What an interesting thing to do. Perhaps we'll try just one more and then call that quits for this video. Let's try it. Well, here we go. We'll try a true curvilinear asymptote this time. Let's do y minus x squared, and let's do y minus 4 and x plus 2. I'm making these up as I go, seriously. None of this is exactly planned. I like to ad lib, and I like doing, the reason you're getting a number of these is I like doing them. And I encourage you to try to experiment and enjoy them as well. But by experimenting and playing, you get to discover some principles about how graphs work. And this is a privilege I didn't have when I was growing up. There was no internet and no Wolfram Alpha site to practice on. So all of these had to be done by hand. Slightly more different prospect. But let's continue. Let's do this first. X equals negative 2 will be an asymptote. Y equals plus 4 will be an asymptote. And, oh, I didn't plan this, but y equals x squared is going to go through this point. Well, there we go. Let's probably just as well. We'll learn something new. Okay, so we have, pardon the slight bulge in that, it's just not my drawing skills on a whiteboard. So we have three asymptotes. We have one vertical, one horizontal, and one curvilinear. Now, just out of curiosity, let's duplicate this one. So how will we duplicate it? We will get the y minus 4 and square it. By the way, if I made this a power 4 or 6 or 8 or 10, it will have the same effect. It will distort the shape of the graph near the asymptote, but it nonetheless will behave like a mirror. If it's an odd power, like this is to the power 1 and this is to the power 1, if I tripled this, for example, it would look much the same, but the curve would distort slightly, but it'll be in the same locations. I'll leave it like that. Now, actually I was using red as the mirror, so we've now mirrored the y equals 4 asymptotes, so let's put a little red line. My red is becoming tinged with black, but there we go. The first part of our hyperbola is going to be here. So it's going to be asymptotic at x equals -2, and it's going to be an asymptote to the curvilinear coordinate y equals x squared. Now I think you can see instantly we have a mirror here, so the next part of the curve is going to be trapped in there. The exact shape of it is something that we'd need to investigate more thoroughly. There is no part of the curve here, and that part, because this is a mirror, there'll be no part here either, which means all of this. So let's move over to this side. There'll be no part here, but there will be part here. This is behaving like the chessboard. And because this is a mirror, there's going to be a portion here. And you can see it matches up chessboard like down here. Normal asymptote, normal asymptote. So there'll be a gap and then the graph will appear again. So that's what our graph will appear like if we duplicate this particular asymptote. Now if we had duplicated another one, like this one, actually let's explore that. Let's imagine, no look, I'll use purple. Let's imagine we duplicated this one so that this also became a mirror. Right? Then obviously this all behaves the same, but something different is going to happen on this side. So let's explore that. This is now a mirror to that, so we're going to have a little bit of the graph in here. Because that's a normal asymptote, we won't have any here. Because that's a mirror, it won't be duplicated. Because that's a mirror, it won't be duplicated. And also, because that's a normal asymptote, we don't expect anything on the other side of a graph anyway. So that's how the equation would change if we duplicate that. You've come on a long journey. If you've watched all my videos, you've been discovering graphing principles for hyperbole and asymptotes and more complicated functions and then relations. We've looked at how we can have oblique and curvilinear asymptotes, and now we've looked at what happens when we duplicate them, when we have powers of 2, 3, 4, 5, 6, 7 applied to these various terms. What a huge effort. By the way, if I change that to -4, then the graph would disappear from these three places and appear in all the others. I forgot to, that's something we did a number of videos back, looked at the effect of a negative constant. My goodness, what a journey. One more to go. The next video I show how it all fits together with polynomials and zeros and such like. And I encourage you to watch that. If you've enjoyed this and you're new to Crystal Clear Mathematics, then please subscribe so you can find out about the future videos. And I would most certainly encourage you to like the video and to comment. I always enjoy getting your feedback. And as always, I thank you very much for watching.